Algorithm for single-source multiple sink markets. In this section, consider the special case of a flow market, market 1, with a single source and multiple sinks. We will assume that the underlying graph is directed. In case it is undirected, one can use the standard deduction from undirected graphs to directed graphs. Replace each undirected edge UV with two edges UV and VU of the same capacity. Formally, let V equals VE be a directed graph with the capacities on edges. As in V, the source node and T equals to the T1, T3 until Tr be set of sink nodes, also called terminals. Let Mi be possessed by sink Ti. The problem is determining equilibrium flow and the edge prices. The following example may help appreciate better some of the intricacies of this problem. Example 5.7. Consider graph V equals to VE with V equals to the set S, A, C, D, and the sinks B and D with $150 and $10 respectively. The edges are SC having capacity 2, AB have capacity 1, and the AD, CD, CB having capacity 10. See figure 5.5. The unique equilibrium prices are P of A equals to $10, P of AB equals $30, PS equals $40, and the rest of the edges have the price. At equilibrium, flow on path SAD is 1, on SAB is 1, and on SCB is 2. Simulating the algorithm below on this sample will review the complex sequence of cut needs to find in order to compute the equilibrium. Computing equilibrium for other values of money is left as an interesting exercise. We will present a strongly polynomial algorithm for this problem, which is based on the primordial schema, i.e. it alternatively adjusts flows and prices attempting to satisfy all KKT conditions. Often produced algorithms can naturally be viewed and execute auction. This viewpoint is lead to particularly simple way of presenting the correct algorithm. We will describe it as an assigned price auction in which the buyers are sinks and the sellers are edges. The buyers have fixed budgets and are trying to maximize the flow they receive, and the sellers are trying to extract as high a price as possible from the buyers. One important deviation from usual auction situation is that the sellers act in a highly coordinated manner. At any point in the algorithm, all edges in a particular cut, say S bar, raise the price simultaneously while price of the remaining edges remain unchanged. The prices of all edges are initialized to 0. The first cut considered by the algorithm is the unique maximal mean cut separating all sinks from S, say S0, S0 bar, denoted by rate of Ti, the cost of the cheapest Ti path with respect to current prices. The flow demanded by sink Ti at this point is Mi over rate of Ti. At the start of the when all edge prices are 0, each sink is demanding infinite flow. Therefore, the algorithm will be able to find a flow that satisfies all demands. Indeed, this will be the case all the way until termination. At any intermediate point, some cut will need to be oversaturated in order to meet all the demands. The price of edges cut S bar is raised as long as the demand across it exceeds supply. The cut is oversaturated because of flow demanded by sinks in S bar. At the moment that demand exactly equals supply, the edges in this cut stabilize and declare themselves sold at current prices. This makes sense from the viewpoint of the edges in the cut. If they raise prices anymore, demand will be less than supply. The cut will be undersaturated, and then these edges have to be priced at 0. The crucial question is, when does the cut S bar realize that it needs to sell itself? Then it is reached as soon as there is a cut, a U bar with S, which is a subset of U. Such difference in the densities of the two cuts is precisely equal to the flow demanded by sinks S bar minus U bar, figure 5.6. Let U bar be the maximum such cut, it is easy to see that it will be unique. If U equals V, the algorithm holds. Otherwise, cut U bar must be that. It must be oversaturated. It assumes the rule of S bar, and the algorithm goes to the next iteration. Note that an edge may be presented in more than one cut whose price is raised by the algorithm. If so, its price will be simply the sum of the prices assigned to these cuts. Suppose that the algorithm executes k iterations. The SI/SR be the cut. It finds in iteration I 1 less than equals to I less than equals to k, with sk equals to v. Clearly, we have S0, which is a subset of S1 which is the subset of S2, and so on, which is the subset of Sk, equals V. Let Ti be the set terminals Si minus Si minus 1 for y less equals I less equals to k. Let Di be the set of edges of G because I bar for 0 less than equals to I less than k, P be the price assigned to edges in Ci. Clearly, for each terminal T in Ti, rate of T equals to P0 plus P1 plus P2 and so on plus Pi-1 for one thing equals to I less equals k. Let G prime denote the graph obtained by adding a new sinc node T to G and the edges EIT each of the original sincs to T. Let the cost of HIT be Mi or rate of Di. For the instance, even in G prime, we will denote V minus S by S bar. It is easy to see that each of the cuts Si bar union the sub T in G prime has the same capacity. For 0 less than equals to I less than equals to k, and each of these k plus 1 cuts is a minus C cut in G prime. Let F prime denote maximum ST flow in G prime. Obtain flow F from F prime by ignoring flow on the edges in T. Then F is a simple flow in G that sends Mi over rate of the I flow to each sinc Ti. Level 5.38. Flow F and the prices found by the algorithm constitute an equilibrium flow price proof. We will show that flow F and the prices found satisfy all KT conditions. Since each of the cuts Si bar union the set of T for 0 less than equals to I less than k is saturated in G prime by flow F prime. Each of the cuts C0, C1, C2, Ck minus 1 is saturated by F. Hence, all edges having non-zero prices must be saturated. The cost of the chip path to terminal T prime in capital T is rate of T prime. Clearly, every flow to T prime uses a path of this cost. Since the flow to Prime in T is Mi over rate of T prime, the money of each terminal is spent. Below we give a strongly polynomial time subroutine for computing the next cut in each iteration.